Hello, and thanks for joining me on this quick overview of IP, where we include topics like MAC addresses, IP addresses, ports, network address translation, and subnets. Let's get started. First, let's start with a quick analogy that we're all familiar with. When we want to send some information, like a letter, to our girlfriend, how do we do this? So let's start. We live in a house. What does the house have? So we have to go over here and give our house an address. So we know already that the house has a physical address. So let's just make up an address, 321 Oak Street. Okay, so this is the physical address. Included is the city and the zip, and we'll just ignore that for a moment. Okay, so I put that as the from address on my envelope out to the letter to my girlfriend, and I put it in the mailbox and nothing happens. Why? Well, because it's missing some information. So how do we get it to the girlfriend who's all the way over here, and that's our destination? So to get it over there, we need to put the from address, 321 Oak Street, whatever the city is. Oh, wait, now we need a to address. So what is the girlfriend's address? So over here, the girlfriend lives at 111 Lois Lane. Okay, and some city and state and other information. Okay, so then the to information down here must contain 111 Lois Lane. Okay, I send it into the mailbox and it still doesn't get there. Okay, why? Because she lives in an apartment complex. There are a lot of people that live in this apartment complex. Not all of them are my girlfriend, just one. So how do I choose one person in particular to receive this and not everyone else? Well, it would be helpful if it was an apartment complex to put her last name and maybe the house number. So we're going to put her last name, which is, we'll just make up something, Smith. Her last name happens to be Smith. Okay, so that's further information over here because the Smiths live in this apartment complex, and the Joneses, and many other people. Those are all valid addresses, but we don't put all the valid addresses. We only put the one that we're interested. Okay, we put Smith. And we send it along. Still not great because we didn't say who it came from. What if it is received and we want to know that she received it? She's got to send it back to us. If she doesn't put our name on it, maybe she doesn't know who this came from. Maybe she has a secret admirer other than us. So let's put our name on it over here as well. So we're going to put, I don't know, we can't be the Smiths or the Joneses. Let's just be the Bobs. Okay, so we've got now the from, which is synonymous with our original location, and the to, which is synonymous. And then the mailman refuses to move it unless it has postage. Oh, okay, I got to put postage on it as well. Okay, so this is a scenario that we're very familiar with. Now let's translate this into an IP network. So I'm going to switch to blue for IP. Okay, what is the street address of our computer? Our computer wants to send a love letter to our girlfriend over the IP network, maybe over the internet. So what is the address of our computer? Well, if we look it up, it's called the MAC address. The MAC address is the physical address of our device. Let's make up a MAC address. I'm going to put in 111111, and now I make up something 000001. Okay, so first off the bat, you'll notice that the MAC address looks a bit different than an address you might be familiar with. It has to be separated by colons. There has to be exactly 6 numbers. They are hexadecimal, which means they could be from 0 all the way up to F. If you don't know what hexadecimal is, let's just take 30 seconds to refresh what is a hexadecimal number. So normally we've got numbers over here that are what we would normally count as, which are called decimal numbers. And decimal numbers, we know them from 0 all the way to 9. So those are decimal. Deca is the prefix meaning 10. There are 10 individual numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 equals 10 in total. Why? Well, we have 10 fingers, so, and maybe that's why, if you look into it. Okay, what about hexadecimal? Hex, you may be familiar with hexagon or other things that have the prefix hex that means 6. And hexadecimal hexadecimal. So somehow it's 6 plus 10. 6 plus 10 means we have 16 total individual unique elements. We have 0 through 9, and we have more. We have A, we have B, all the way up to F. So that's why hexadecimal all the way up. I see my face is in the middle, in the way for a moment. It's all the way up to F there. Now you can see that I wrote an F back there. Okay, so now we know what hexadecimal is. We've got additional digits. There are unique digits. So when we count with our fingers, we get up to 9, and then we run out, and then we have to start duplicating the digits. We get into the 2-digit numbers when we reach 10. Hexadecimal doesn't have that problem. You have to get all the way up to F before you run out of digits. So the first duplicate or 2-digit extension in hexadecimal is 10. Well, it looks like 10, but it's hexadecimal 10. It's not 10 apples. It's actually more than 10 apples. It's 17 apples, because when we reach a limit of individual digits, we have to add in a second one, and we reset to the bottom. So just think of that. When we count with our numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we ran out. Now we go to 10, which is cycling back to the beginning and doubling up. Same thing happens with hexadecimal. You reach F, and then you got to cycle back to the beginning, and you got to start doubling up. So F is the maximum character. Okay, so that's our street address. And that's a quick review of, or new information for a decimal and hexadecimal. Okay, so my family name is the Bobs. Okay, and that is my IP address. The internet protocol, right now we'll consider IP version 4. So there are different versions of the IP protocol. Just know that right now, if I don't say it otherwise, I always refer to version 4. And my address, I'm going to make this up. So it's 192.168.1.101 is a pretty common IP address. In fact, your computer right now or phone watching this video may be at this exact IP address. Okay, so that's on the outside of the from here. The from contains additional information. It contains my source address, my MAC address, my source logical address, my IP address, and oh no, that's not enough information to get it there. I need a port number. So we haven't really considered ports up until now. The port is the person that is sending this. There may be multiple people that live in the family of the Bobs. So my last name is Bobs with an S. My first name, not very creative, is Bob. Bob Bobs. That's my first and last name. So that is my identity. That is my name. On an IP network over here, we have to give that as a port number, and that is a port. There are different protocols for port, but right now we're just going to assume that it is a port. And I need a number, so I'm going to make up some kind of a random number, 65,001. Okay, so that's my port number. Why is the port number important? It's important because when someone sends this envelope and it arrives at the right apartment complex, it has to go to the right house or unit. Then when it arrives at the right house or unit, it has to go to the right family. That's my family name, Bobs. And then it has to go, maybe there's 100 Bobs, and it has to go to the right individual person, and that's the port number. It's the service or the application that is waiting for this information. The service or the application is the port number. Okay, over here in Lois Lane, what is the specific person? That's the girlfriend, so I'm just going to say Jill. All right, so that's the port over there. And if we translate that into an IP, what is her port number? It's probably 80, because this is web traffic over the internet. A lot of traffic is over the web, the World Wide Web, and it's generally port 80. It's secured now, which is 443, but let's just assume it's unsecured, unencrypted. So port 80 it is. What is her logical address? That's Smith's. Jill Smith is her name. So that's her IP address. So hers is 192.168.1.33, making up an address here. And there's another device on her network. It's her printer, 168.1.34. So you see that I have to be careful now to specify the right IP address. And she also has port 22 for an SSH or a console. She has port 21 for file transfer. She has port 8080 for proxies. And so you see that there's lots of choices, and I have to choose initially the right one. So Smith is going to go to 192.168.1.33. And the MAC address, well, we don't even know what her MAC address is. In this case, it's not as important. Let's think. When you go on a road trip and you go to visit Disneyland and you live in, say, New York State, what do you type into the GPS? You type in your destination address. That's like the IP address. That's the logical address. It's the high-level address. It's the far-sighted address. Where do I go? But in order to get there, there are many mini addresses. There are many short-term addresses. These are the turn-by-turn directions that the GPS will help you with. Turn left. Go on to Route 66. Go on to Route 84. Go on to Route 21. There are many roads to get to this destination. The road is like the MAC address. It's like the very short-sighted address to get me there. If we both lived on the same street in the same geographical area, then I could use her MAC address and it would be enough. But we don't. She lives very far away, so I need to use a high-level or a far-sighted address, which is the IP address. So I don't need to put the MAC address on this envelope. I do need to put her MAC address. I need to put the port number I send from, 65001. I need to put the IP address I send from, that's my name, my last name. I need to put the MAC address of my device so that at least the network takes over, the GPS takes over, as they're called routers on an IP network. You can think of them like the GPS. It takes over, it routes the information, it gets it there. So we do have to put her IP address, and we have to put her port number, which in this case is 80, which was the equivalent of putting Jill up here. Okay, so the source, I have port number, I have IP address. Yes, MAC address, but we won't focus too much on that. The GPS takes care of that. Destination, source, destination port number, destination IP address. Okay, and then hopefully the network gets it there. On a good day, the network will deliver this information. Now, somehow it goes through the network in the middle, and when it sends, it goes over here, and then it reaches a device called a router, and it goes over here, and it reaches another router, and it goes over here, and there's this soup of devices in the middle until it finally arrives eventually at its destination. Each of these routers is an address that is some kind of MAC address. So that's really where the MAC addresses come. They choose the next router, which then puts the next router, which only knows the next router. These are those short-term, turn-by-turn addresses to get to the destination. It's the IP address that they always don't lose sight of. Every single router along the way, oh, he's going to Disneyland, he's going to Disneyland, he's going to Disneyland. And that way they get the routed information where it needs to go. Okay, so that seems pretty simple. If he's in, or in this case, the girlfriend is in a local network, everything seems to work as we would want it to. However, now we have a problem. The problem here is that she's not at this address as far as we can tell. 192.168.1.33. This is unknown to us. In fact, she doesn't know it herself. Bear with me a second, because it gets a little bit more complicated. It seems like it's simple, and then it gets worse. Okay, so let's look at this illustration up here. Here I am on a cell phone. I'm outside of this hotel. What is my cell phone number? It is some kind of a 1-800 number. 1-800-555-1212. So this is my cell phone number. Okay, it's a public number. This is in a registry. It's publicly available. Everyone could find this phone number if they wanted to. Okay, now, when I call to the hotel, I don't want to reach the hotel. I don't want to talk with the staff. I want to talk with someone in this room right here. And what is this room? It is extension 101. So this is the address of the room I want to reach, 101. Can I dial 101 on my cell phone? No, because this is a private extension of a private phone in a private room in the hotel. So instead, what do I must dial? I must dial the outside phone number of the actual hotel, 1-800-111-1234. So I dial the actual outside phone number of the hotel. The phone rings at the front desk. Hello, How may I help you? Yes, can you transfer me to, and then I name the person I want. And they look up, based on the name I give them, the room number. They don't tell me the room number. I don't know the room number. I only know who I want to reach. My girlfriend is traveling. She's in a hotel room, and I want to catch up with her. So he will transfer me, hopefully. This is dependent on him. This is nothing I have control over now. The hotel clerk person at the front desk, they understand my request by giving a name. They've translated that name into an actual room number. This is called address translation. And on an IP network, it's called network address translation. I need to convert one address into another address. I give them the name. They transfer me to the room number. Now I'm on a call with room 101, but I don't know the room number unless I ask them and say, hey, can you please tell me what your room number is? But all I know is that I'm on a call with the outside phone number of this hotel. And then likewise, all they know is that they're on a call with the phone number of my cell phone. Now, my cell phone is not a large business, so it's just me, so it's just one individual. But the hotel, it could be hundreds, even thousands of numbers hidden behind the outside number of the hotel. So let's go to the IP world now. My phone is my house, just like below. So my phone is the same address, 192. Let's just be consistent, 168.1 dot, and I committed to 101 before, so let's not change that. Okay, that's my actual address, but that's not really how the internet sees me. This is no good. Because that is the equivalent of a room number. That's the private address. We talked about private addresses a moment ago. Okay, what does my phone have? It has a public phone number. So because my phone has a public phone number, I have a public IP address. An IP address in a registry in a very special range. So my phone number might be 1.2.3.5. So this is somehow very different than the address I really have. This is really my address. If I go to a tool on my device and say, what is your address? This is my address, but as far as the internet knows me, I've already been translated by my router. So when you connect to a Wi-Fi router, the Wi-Fi router has two addresses and does the address translation for you. So the hotel is like a Wi-Fi router. 100 devices connect to this Wi-Fi router. Each device is given a private address, like my 192.168.1.101. That's my real address, but it's my private address. The public address is what the router has built into the Wi-Fi. And that's what actually talks to the internet. And everyone on the internet, when they see me, really they see the outside address of the router, same as the hotel. They see the outside address of the hotel. So I've got an outside public IP address, really 1235. Now, similarly, the hotel has one, 1.2.3.4. Okay. Now, can I communicate? If I'm an address 1235, can I talk? Can I call? Can I type in the digits 1234? Yes. And then what happens? Now over here, the room number is 101. And that's the equivalent of a 192. Let's see if we can fit it in here. 192.168.1. It's room 101. So you know what? Maybe they give the IP address the same as the room number. That might make sense. Just to keep things straight here. So we'll get rid of this. Okay, so now we have the actual room number as well. Okay, so on my phone, I dial the public phone number, the IP address of my destination. I ask them for my recipient. That's Bob. That's the port number. That's why the port numbers matter. So here in the actual table, the front desk has a little table, and he says, what was her name? Jill. He says, when anyone asks for Jill, that means 101. Jill equals 101. Or more specifically, he takes that off and he says, okay, what does Jill actually mean? Jill means 192.168.1.101. So he knows this. Now, tomorrow, that may not be the case. Maybe they reallocate all the addresses. Do they have to talk to the internet? Do they have to work on a standards body? Do they have to coordinate with anyone outside of their hotel? No. They're free to change these numbers whenever they want to. So that's why they're private. They're free to assign, you don't have to pay anyone for them. And there's no reservation sometimes. They can change on a moment's notice. But for right now, his list says Jill does equal 192.168.1.101. So whenever I call in and whenever I ask for Jill, he will translate that into that IP address. But it doesn't show on my side. I completely don't know that Jill is really at 192.168.1.101. All I know is that Jill is at the outside public phone number, public IP address of the hotel, and vice versa. Jill, ring, ring, ring. Hello, who's this? Oh, it's my boyfriend. What does she look like on the screen and see? She doesn't see my 192 private address. She sees my public address. So both sides only see the public address of the opposite. Both sides network address translate based on the port number, and the port number here in this analogy is the person's name. So they call in, they give the name, and they get translated to the port number. Okay, so on the internet now, over here, just to finish the thought, here we have this Jill destination we try to reach. This is Jill's router right here, the one that gatekeeps her house. So all of her Wi-Fi devices are somehow hidden behind this router. What is the public IP address of this router? 1.2.3.4. So when I send the letter, as I had before, I can't actually put down here 133, even though that is really her address. Instead, you may have just guessed it. I put in the 1.2.3.4 address. There. Now it actually goes from my public address to her public address, which is her router. And that network address translates based on asking for port 80 internally to a web server where Jill is waiting and receives the information. So now you can see the correct information on these packets. And just also keep in mind that the packets change. The information on the headers, the information on the outside of the envelope changes with every hop, which means every device it goes through, it hops to the next one, and they rewrite some of the information. What is rewritten? The MAC address is rewritten, source and destination. Every hop, the rewrite of the IP or the frame header happens where it rewrites the source MAC address and the destination MAC address. Remember, we don't worry too much about this. This is just the turn-by-turn directions to get there. And then what is the logical address? That is the IP address. That remains on all the packets from source to destination because that is where I try to go. And the port numbers remain on all the packets, unless there's some fancy proxy in the middle. But generally, the port numbers stay the same. I'm port number 65,001, and she's port number 80. And then when it arrives, she says, where did it come from? And then it's a particular IP address and a particular port. Okay, this process of taking a letter and putting it inside an envelope and then paying for postage, the postage in this analogy is the protocol overhead. So I'm just going to say headers. The headers are cost. They consume bandwidth on the network. So you do have to consider those when you're considering bandwidth because that is the postage in order to get it from one end to the other. So the ability to take a letter, put it inside of an envelope, seal the envelope, put that envelope inside of another envelope, seal that envelope, put the stack of envelopes inside of another, and you just keep putting it inside and inside. It's called encapsulation. Encapsulation is the process of taking data, that's the letter, putting it inside an envelope, that's the protocol overhead, that's the headers. They identify things like source address, destination, is it encrypted, does it need to go fast or slow? These are the additional things that get wrapped around it. And then it goes inside of another envelope, which goes inside of another envelope, and it gets from one side to another. The stack of envelopes, depending on where you look at it, it's called the packet. The packet is the IP information and then everything contained inside of it. If you were to open that envelope and look inside, there's another envelope that's called the frame. The frame has a source and destination address for the header and footer, and that's another envelope. And if you tear that envelope up, finally inside you get the letter. That's the love letter that's actually written from one side to the other. But it's a rabbit hole. IP goes inside of another envelope, which is the port number envelope, which might go inside of another envelope, which might go inside of another envelope, but generally there's a finite number of envelopes, and generally it's only about 5 or so, in most cases, envelopes that get encapsulated to get the information from one side to the other. Okay, that was a lot of information, and we still didn't talk about subnetting, so let's just do a quick overview on the subnetting, and we'll be finished. So first of all, we know already about the decimals and hexadecimals, so let me just get rid of that information here. All right, so a subnet is kind of like a grouping of devices. Let's go back to the physical side and then translate it as we have been. So first of all, let's see. So Jill is over here. That's her house. There's another house, and there's another house, and they're all contained within some geographical boundary. So we know this is a zip code. If we send something and route by zip code, it gets there very efficiently because geographically there is already a known area of housing. And if you get it to the right zip code, you're already halfway there. You've got it very close because the entire continental US is divided into these geographical regions. All right, so over here, this computer down here, he's in some kind of a network, and there's another printer, and there's a router, and there's a PlayStation, and there's an IP camera, and there's a toaster oven. All of these devices, however, are contained within the geographical region of the house. So if we gave the house and the houses on the street a geographical number, like a zip code, then we could very efficiently route from New York to California, or from California to New York, because the zip code would already identify it's New York. And maybe the zip code identifies it's a particular county, and it already identifies a city, and it already identifies a neighborhood. So these create very efficient ways of routing information. Think of a pizza delivery. So we have a pizza delivery boy here, and he has to deliver the pizza, and his company wants to make an advertisement. Where would you send this advertisement? It would be a very long list to itemize all of the houses in an area surrounding the pizzeria. So instead, they can do what's called a mass mailer, and they can pay their post office to send this. It's junk, but it's nonetheless information to all of the surrounding houses. We have a great deal on pizza. You get 2 for 1. So they think that this is somehow a great deal on pizza. You get 2 pizzas for the price of 1. They want to send this broadcast out to everyone in their geographical region. A pizzeria in New York State would not want to notify anyone in California. That's too far. That's outside of its boundaries of influence, outside of where this information would be applicable and where this information would make most sense. So he sends it only to his broadcast domain. A broadcast domain on a computer network is the geographical boundaries of these devices are kind of near each other, so they're going to share the junk messages together. If someone is not in their broadcast domain, they're too far away, they're like in California, and then it would be too far for this information to get. Since it is an advertisement, most people consider it junk. I mean, how many pieces of junk do you get in your mailbox? So most people consider this junk messages, and they throw it out into the trash. But a couple people, that's actually pretty helpful information. I've got a party, and I might take advantage of this. So a broadcast is generally junk for most people, and a select few, it's actually really good, important information. But if you were to send a broadcast of a pizza deal to the entire US, and every pizzeria were to do that, no one's inbox would have any more room. It would be completely filled with junk. So it creates these pockets of junk, these pockets of momentary broadcast information that are applicable to some and not others. Okay, let's take that into the computer realm as well. So maybe up here, this is the zip code 1111, and over here we have some kind of a broadcast domain, which is the zip code 2222. All right, so we've divided them up. So now when my printer powers on, it sends a broadcast or a junk message. Hello, I'm a printer. Here's my MAC address. Everyone on the network would get this. My computer would be like, I'm gonna store that in case I need to print something to you later. And the router, I'm gonna store that because I like to know all the devices on the network. But the PlayStation probably doesn't use the printer, so that's junk. The toaster oven, The refrigerator that has the built-in TV screen probably doesn't need to know the printer's MAC address, junk information. So we've identified that some, take note, like my computer needs to know how to find the printer and the router, but to the other devices on the network, it's junk. Okay, so somehow I need to create a division among these computers so that I know which computers are in one broadcast domain versus which computers are in a different broadcast domain. So let's type in the IP address, and I've gotten the wrong color here, so give me a second. Okay, so let's get an IP address going. I'm going to choose my actual IP address. So we've got 192.168, and this is a very typical IP address, 1.101. Okay, now what parts of this IP address will indicate my zip code, and what parts of this IP address will indicate that it is somehow uniquely me and not someone else? So first of all, let's convert the addresses here into the hexadecimal equivalents of these addresses here. And for this, I'll actually go to this right here. And I've prepared a quick illustration of this. Okay, so if I skip to the next slide, just bear with me a second. Okay, so it's 11000. So this 192 happens to be in binary now. We talked about decimal, that was 0 through 9. We talked about hexadecimal, 0 through 9, A, B, C, D, E, F. We didn't talk about binary. Binary is ones and zeros. There's only two, a 1 and a 0. There's no more digits. So remember what happened when we wanted to represent the number or quantity 9? We could do that in decimal because there was a 9. But what about 10? We had to go back to the beginning and we had to double up. Well, binary only has 2 digits, so we run out very quickly where we have the first apple, that's 1. Now the second apple, we have no more digits. 0 is a quantity, 1 is a quantity, that's a total of 2 states. We don't have anything room for the third state. So what do? We go back to the beginning and we double up. So in binary, 1, 0, which looks like 10 to our eyes, is actually 3. Because that's after 2, right? Or I'm sorry, it's 2. I misspoke. And then 3 is what would look like 11, because 1, 1. So if we just do a quick table here, 1 to our eyes in binary would be 0, 1. And then 2 to our eyes would be 1, 0. And 3 to our eyes would be 1, 1. And what's 4? Give you a moment to think about it. What would be 4? 4 would be, well, we run out of digits. So we need another digit. So we cycle again. That's 4. What's 5? 1, 0, 1. What's 6? 1, 1, 0. What's 7? 1, 1, 1. And, we've run out of digits again. So we go to 8. So what's 8? 8 is 1, 0, 0, 0. And we keep going, and we keep going. So binary looks very strange to our eyes because we're used to counting with 10 digits. In binary, you only get 2 digits, which is very convenient. A light switch can be represented in binary, 1 for on, 0 for off. And now we have a way to represent state. So I'm going to write 192 in binary. 1, 1, 1, 2, 3, 4, 5, 6. All right, that way I count the right number. What's 168? So I got to go to my little cheat sheet here. You can do it with Windows calculators and stuff. In this case, I just want to make sure I get it right. So I go to my Windows calculator and I somehow type in the number and then I switch it from one to the other. So it's 10, 10, 10, 00. So let me type in that. 10, 10, 10, 00. And then what is 1? 1 is really easy to convert into binary. It is 0, 0, 0, 0, 0, 0, 0, 1. Now it's kind of hidden behind me there. And then what's 101? It's whatever it is. So we can keep converting, but I've written enough for you to get the idea I'm trying to give you. Okay, now we need somehow a way to draw a magic boundary line to divide this into two pieces. Now, they don't have to be equal pieces. They can be disjointed pieces, but pieces nonetheless. Anything to the left is that zip code. So if we draw the line right here, then the IP address, which is really drawn right here, if I line them up, right, there we go. Okay, so here we have it divided, and on the left-hand side, we have the portion that chooses the zip code. So this is choosing zip code 192.168. And then over here are all what's called the host addresses. And this is what is it going to identify one computer versus another computer. So carefully and cleverly, we have encoded or hidden inside an IP address additional information. It's not just my phone number, like the 1-800 number of my cell phone. The fact that it starts 1-800, that means something special, even on a telephone network. That means you are going to get a toll-free number. So that's it's got a reserved range, and it has special meaning. And then 555 has special meaning. And then 1212, finally at the end of the number, we have the individualized phone that it represents. So the same thing here, 192.168 represents the zip. In this case, it could be divided differently. And the 1.101 represents my computer. So let's have a look here. I take the 192.168, I write it in binary, and I divide it right in the middle. And in order to signal where the red line was, I mean, the red line could have been here, it could have been here. You could do it in between the digits too. The red line could have been right there. So wherever you draw the line, you have to indicate somehow with a 1. And when the ones stop, that's where the line is drawn. So we're going to draw some ones here. 1, 1, 1, 1, 1, 1, 1, 1, dot, 1, 1, 1, 1, 1, 1, 1, 1, dot. Okay, we reached the line. When we reach the line, we stop drawing ones, we do zeros. So 0, 0, 0, 0, and all the way to the end. So a subnet mask is what we've just, in fact, learned. A mask is a way of dividing something. In this case, you could think of a mask as, right now, why do you see a circle around my webcam? I created a circular mask. All the rest of the information on the webcam is hidden except what's in the circle. It's a circular mask. So some information is revealed, some information is hidden. In this case, the mask, some information is important, some information is not important. We need to determine what the network address is for this network, and we need to determine what the host portion of the address is, who is the individual computer. So all a subnet mask is, and now I'm going to write that here, that this is a subnet mask. Okay, a subnet mask is a dividing line, an imaginary dividing line, that divides an IP address into two chunks. Those chunks do not have to be the same. And the left-hand chunk identifies the zip code, the geographical region. It doesn't have to be geographical on an IP network. It could be on the other sides of the world, but just go with me here that generally they're computers that are physically near each other. And then on the right-hand side, it is the individual device, and that is the unique identifier to divide one to the other. The subnet mask is just a dividing line, so I know which side of the IP is one and which side of the IP is the other. And the mask is always consecutive, not interrupting. 1, 1, 1, 1, 1, 1. They stop, and when they stop, the zeros, 0, 0, 0, 0, 0, 0, and then they start. What is the number represented by 1, 1, 1, 1, 1, 1, 1? 8 ones. If we go now from binary and convert back to decimal, how we would count, that number happens to be 255. So 255, now there's a dot, and then there's a bit more in the mask. Right now we're just looking at the red portion. 1, 1, 1, 1, 1, 1, 1. Okay, that's again 255. Okay, and then remember when it stops here, and then the zeros start. How do you convert 0 from binary into decimal? That's simple, 0, and then 0. So when you see a mask 255.255.0.0, that is indicating where you draw the magic line. And it's not obvious to our eyes where the line goes unless you convert to binary. So you have to take the IP address, you have to convert from decimal into the binary like I've done with the ones and zeros. And then you line up the mask, which is also converted to binary, just like I've done. And then you literally draw a dotted line, slicing the 2 in half. And everything to the left-hand side is going to be the host address or the network address. And everything to the right-hand side is going to be the host address. That's the individual computer. So a subnet mask sounds scary. It looks complicated at its onset. All you're doing is taking an IP address, which is an address, like the Bobs, like the Smiths, like the Joneses. You are representing it in binary form, which is no more complicated than just converting from one format to another. It's not changing the information value, it's just changing the way it's presented. Then lining that up with the mask and looking where there's imaginary breakpoint, where do the ones stop and where do the zeros start, drawing a line there, and then reconverting it back. And therefore, when we convert it back, here I've already done it, 192.168 is the network side, and 1.101 is the host side. I knew to divide them up right there in the middle because it just happened that our red line here was in the middle. But again, they don't have to be in the middle, and you can divide it. Let's think about, just quickly, the different divisions. If I move that dividing line to the left, like right here, what if the zip code was 192? Then I can fit more computers in that because I've given now the last 3 bits to represent the host side. If I move the line to the right, then I have more networks and less hosts. So that's the trade-off. There's only a certain finite number of digits, 4.3 billion. Of those 4.3 billion IP addresses in IP version 4, we have a finite number of networks and a finite number of hosts. So I have to choose my dividing line carefully. But generally, in an organization, you don't need billions of computers. You might only need 1,000 computers. So you can be very generous on your network side and move it way over to the right. But if you're an internet service provider, you may need to move it back over to the left because you may have many, many more hosts. Okay, so hopefully that was a quick, clear, and concise overview. We talked about what is an IP address, like your last name. What is a MAC address, like your device's physical address, which never changes. The IP address can change, but the MAC address, it never changes for all intents and purposes. And the port number, on my side, that's where I send from. That identifies me, the person. The port number on their side identifies them, the person, so we can exchange and sometimes network address translate the addresses. That's why the port number is important. And then finally, for efficient routing, so that my inbox doesn't get clogged with junk, I might be in the 192.168 subnet by the division of the mask, which is 255.255.0.0. So that's the mask division. And therefore, I'm in the 192.168 subnet. And therefore, a printer that is not in that same division, not in that same subnet, would not send me any junk information. Even if it's physically sitting next to me, I would not receive the junk it sends because it would be in a different division, in a different grouping, in a different way of organizing these. So all of this complexity is just to organize things in a very efficient manner. And it's really logically organized in very similar ways that we've seen analogies in a house, in a hotel with phones, and in a road trip with a GPS. So if you think about those analogies, it tends to help to make this a bit more clear and understandable. All right, well, thanks so much for watching. Hope this was helpful. I'll see you in the next one.